So we have taken a problem setting where D is D1, D2, D3, so on. These are the training examples. PM are the training examples. Here, DI is generated by adding some noise or error to the function of x, to the function of x. And here, what we are trying to do is the mean can be calculated from this function of xi, function of xi. In other words, in our problem, it is h of xi, hypothesis of xi. And based on this, we started our derivation for likelihood. What is likelihood? In Bayes' theorem, what is Bayes' theorem? In this equation, which is likelihood?
P of D by H.
Probability of data given by hypothesis.
Yeah, probability of data given the H. We should not say by, okay? Probability of data given the H. So, this is called maximum likelihood. And we know that probability of H is called
Prior probability.
prior probability, and probability of H given D is called posterior probability. So, in maximum likelihood hypothesis, what we want is the hypothesis which will return the maximum probability, that we call as maximum likelihood hypothesis. So, probability of data given the hypothesis. So, we have so many hypotheses here. Among the hypotheses, which will return the maximum probability of the likelihood, we call it as maximum likelihood hypothesis. So, because we know that when we want the probability of data is depending upon di, d1, d2, d3, d4, so on. So, we take the product of all these probabilities. So, it is equal to argmax H belongs to H pi the product of probability of D given Di given the H, where I is equal to 1 to m, where I is equal to 1 to m. Here we made an assumption. We made an assumption. What is our assumption here?
Data
That
follows normal distribution.
yeah, data distribution follows normal distribution. Normal distribution. Normal distribution is a bell-shaped curve with mean 0 and standard deviation 1, and the probability density function PDF is given as 1 by 1 by square root of 2 pi sigma square e to the power of minus half xi minus the mean by sigma whole square. That is the probability density function of the normal distribution. This is a standard formula. Now substituting this in our maximum likelihood hypothesis, maximum of I is equal to 1 to m. Here it is di, the probability of di, minus the mean. What is the mean here? The hypothesis of
xi.
xi by sigma whole square. Now, because in the mathematics, whenever we want to maximize a function, we can take logarithms also. When we take logarithm of a into b, it is logarithm of a plus b. So when we take logarithm of pi, it becomes the sigma. So we are trying to maximize, let us to maximize this value, which is same as the maximizing the logarithm. Natural logarithm ln. Remember, general standard notation is log represents base 2, ln represents natural logarithm base e. Both are different. When in ID3 algorithm we calculated base 2 logarithm, not natural logarithm, but here we are taking natural logarithm. So logarithm of e to the power of x is equal to x into logarithm of e. Logarithm of e is equal to 1. So logarithm of e base e is equal to 1. So logarithm of e to the power of x is equal to x. So here this is log of these two terms. So AB again, so maximum likelihood hypothesis is equal to the maximum of h belongs to h. Instead of pi, the sigma I is equal to 1 to m. The first term is logarithm of 1 by 2 pi sigma square root, and this is minus half di minus h of xi by sigma whole square. What we can do is we can eliminate the terms which are independent of hypothesis. This is independent of hypothesis. It has nothing to do with the hypothesis. So, and even this 2 sigma square is also independent of the hypothesis. So what we can do is only we are maximizing, we are not evaluating it. We don't want the exact value, we want the maximum value. So there is nothing wrong. We can eliminate the terms. I is equal to 1 to m. The first term is deleted, minus di minus h of xi whole square. Because this is a negative value, maximizing a negative value is same as minimizing the positive value. So the maximum likelihood hypothesis is the minimized value of h belongs to h. I is equal to 1 to m. Minimized value of di minus h of xi whole square. This is same as minimization of least square error, isn't it? Least square error also, what we have done is, in least square error method, we calculated y minus y cap, and we calculated the squigma of all these squared errors and minimized it, which is very same. So from this equation, what we can say is, what is maximum likelihood hypothesis? HML is a hypothesis which minimizes the squared error between the training values. What is DI? Training value. And the hypothesis prediction. Hypothesis prediction. What is hypothesis prediction? H of xi. So what we are trying to do is di minus h of xi. We are trying to minimize the summation of all these squares. This is when a hypothesis gives the minimum value of it, then we call that as maximum likelihood hypothesis, which gives the minimum error. And here the assumptions are important. What are the assumptions? The training values are generated from by adding the noise to the true target value, and it follows normal distribution, and we can maximize we have maximized the logarithm instead of the original function. Any doubts? Shall I go ahead?
Yes, sir.
Yes, sir.
Okay, thank you. So this is what we discussed yesterday. See, derivations you can learn the derivations only by practicing them. There is no other way. The more you write, the more you remember. Seeing, reading, no use in derivations. So please practice them. Please practice them. Right. Moving on to the next topic. So what we found now? What we found? We have found maximum likelihood hypothesis, right? Maximum likelihood hypothesis. How to predict probabilities? Prediction of probabilities using this maximum likelihood hypothesis. That is our topic. By using this, how we can predict the probability. How we can predict the probability. Now, there are some situations. Where the d value or the target function is it takes either 0 or 1. Called non-deterministic function or probability function. What we mean by that? For example, we are talking about cancer patient problem. See, we don't want deterministic probability here. Ante value enta anedi manaki, we are not bothered. The only thing is, if he is affected by the cancer, the value is 0. If he is not affected, the value is 1. We don't want the probable exact value like this here. What we want is either 0 or 1. or in other words, another classification problem, loan approval. Loan approval. So we will take all the credit history. If the loan is approved, the target value is 1. If the loan is not approved, the target value is 0. The target value is 0. And suppose in case of cancer, sometimes it may say that 92% people survive. That means how much percentage they will not survive? 8% not survive the cancer. Then what we say is f dash x, according to this data, f dash x is equal to 0.92, and in 92% cases, f of x is equal to 1 because they survive. In 8% cases, f of x is equal to 0 because they will not survive. This is the problem setting. This is the problem setting. So to develop a learning problem for this type of situation where the target value is either 0 or 1, either 0 or 1. Even if we have some unpredictability like accuracy or only 92% of cancer people will survive, then even in that case, in 92%, the target value is 1 and remaining the target value is 0. So how do we go ahead with the learning problem for deriving maximum likelihood hypothesis? Maximum likelihood hypothesis. So let us say we have a problem set of xi di. Earlier we have taken only di, now we are considering x also, and where xi and di are random variables. So x is something like patient details, patient 1, patient 2, patient 3, and di is whether he will survive or not. If he survives, 1, if he doesn't survive, 0. So d has only two values, either 1 or 0. And now what is the likelihood hypothesis definition? Probability of data given h. This is the definition. And what we can do, we can take this product of all the probabilities xi and di given the h. That particular hypothesis di. Because xi is independent of hypothesis, because hypothesis says he will survive the cancer, and second hypothesis says he will not survive. So this hypothesis has nothing to do with patient. అంటే పేషెంట్ డీటెయిల్స్ వల్ల హైపోథసిస్ ఏం ఎఫెక్ట్ కాదు. సో బికాజ్ xi is independent of hypothesis, and xi value will not depend on hypothesis, di value will depend. So what we can do is both are individual probabilities. So probability of d given h can be calculated as the pi, of course I is equal to 1 to m, I is equal to 1 to m, probability of xi into the probability of di given h. To make it more appropriate for that given xi, So we know that di is equal to 1 if he survives, if h of xi is true. Di is equal to 1 if h of xi is true, and di is equal to 0 if h of xi is not true. So what we can try here is the probability of di given h. We are writing xi here to for that particular xi value is equal to h of xi if di is equal to 1. Otherwise, if di is equal to 0, the probability is 1 minus h of xi. Because it is, when it is 92%, it is 8%, the probability. So the probability of di given h is, when di is equal to 1, it is hxi, h of xi, and when di is equal to 0, 1 minus h of xi. So this, the same formula I can write in a different way so that we can substitute it in the equation. Now let us say the same thing, let us write like this. Probability of the same equation, I am not writing a new equation here, is equal to h of xi to the power of d 1 minus h of xi to the power of one minus di. Now, if di is equal to 1, what is the what does this equation produce? Tell me. Suppose di is equal to 1. What is the value of this equation? Yes. Suppose di is equal to 1. This 1 minus 1 is 0. So this term vanishes. I can write h of xi. If di is equal to 0, then this term vanishes. Anything to the power of 0 is equal to 1. So then the probability of di of h, di given h, is 1 minus h of xi, and 1 minus 0 is 1. So the same equation we represented in this par problem. Is it clear, Pillalu? This equation I represented in this h of xi to the power of di into 1 minus h of xi to the power of 1 minus di. If di is equal to 1, this term goes off. And e answer vastadi manaki. If di is equal to 0, this term goes off, this answer will come. Okay?
Yes, sir.
Yeah. Now, so substitute in this equation now, and because the probability of xi will drop it, okay. The equation we got is the equation, what is the equation we got? Probability of data given h is this is the equation. Now we are substituting the above. This probability of di of given h xi is h of xi to the power d 1 minus h of xi to the power 1 minus di into p of xi into p of xi. And for maximum likelihood, what is the maximum likelihood? The probability of data given h which gives the maximum, the hypothesis which gives the maximum probability. So the maximum likelihood hypothesis for the given setting of the problem where the target value is either 0 or 1, di value is either 0 or 1, in that setting the likelihood of hypothesis, maximum likelihood is the maximum value of h belongs to h one h of xi to the power of di into 1 minus h of xi to the power of 1 minus di into probability of xi. So this can be dropped because it is independent of hypothesis. It is a prior probability. So it has nothing to do with the hypothesis. So we can drop it. Is independent of hypothesis. So The maximum likelihood hypothesis is given by the maximum value of the product of the probability of the hypothesis to the power of di into 1 minus probability of 1 minus di. Did you see this equation anywhere? Did you see this equation anywhere? Something like p to the power of r 1 minus p to the power of 1 minus r. Did you see this here? P to the power of k into 1 minus p to the power of n minus k. Where did we discuss this problem, this equation? In which topic? In which topic? Binomial distribution. Binomial distribution. When we are discussing the binomial distribution, we derived this formula. So this is binomial distribution. Binomial distribution. And to maximize an expression, it is the same as maximizing its logarithm. Maximizing its logarithm. So when we take logarithm, pi will become the sigma. Pi will become the sigma. And logarithm of a to the power of b is equal to b logarithm a. So di logarithm of natural logarithm of ln h of xi plus 1 minus di to the power of, that means, sorry, logarithm where did we see this formula? Gurtunda? When we discussed about decision tree algorithm, I think ID3 algorithm, there we calculated the entropies using this formula. So this quantity where we calculated sigma minus p log pi, ఏమన్నాం దీన్ని? గుర్తుందా మీకు? ఎంట్రోపీ. So this equation is also called, this expression is called sometimes cross entropy. So this is about maximum likelihood. So we derived two equations for maximum likelihood. One in the setting of deterministic probability. This is deterministic probability, and with likelihood least square minimizing error. And then the second equation we derived in the setting where it is non-deterministic probability, like either 0 or 1. In that situation, the maximum likelihood hypothesis is di logarithm of h of xi plus 1 minus di into logarithm of 1 minus h of xi. In case of deterministic probability, it is the hypothesis which returns the minimized error, the difference between the training value and the hypothesis value. So that was equation number 1, if you want to call it, maximum likelihood. And this is equation number 2 for maximum likelihood hypothesis. So this is the final equation. This is the final equation. And this is for a different setting. Both are the equations for maximum likelihood, but the problem setting is different. In this situation, the problem setting is deterministic probability. We can calculate the probability. But here, we are not interested in the probability. We were interested in either 0 or 1. So this is non-deterministic probability. So tomorrow we'll see another theorem called minimum length principle, minimum description length principle. What is Anscombe's razor? Gurtunda? Anscombe's razor. Chadivama manam?